Hello students, welcome back. Today we're bringing you a brand new explainer. We're diving right into Class 10 Science, Chapter 3, Metals and Nonmetals. Specifically, Part 2, where we're going to uncover the chemical properties of metals. In our previous lesson, we covered the physical properties, basically how metals look and feel. But today is a lot more fun. We're going to see how these metals actually behave and react with the world around them. Let's get right into it.
To kick things off, I want you to think about this puzzle for a second. Why is it that a metal like sodium has to be strictly locked away, stored in kerosene oil, completely hidden from the air, while a metal like gold can just be dug out of the dirt, worn as jewelry, and literally stay perfectly shiny forever? Or, why does iron get all rusty over time while other metals hardly change at all? It's a total mystery of behavioral extremes, right? And the answer to all of this lies entirely in their chemical properties. So here is our roadmap for today's explainer. We'll be covering 1. What chemical properties actually are. 2. How metals react with oxygen. 3. How they react with water. 4. Their reactions with acids. 5. Displacing in salt solutions. And finally, 6. The reactivity series.
First up, Section 1, what are chemical properties? Basically, understanding how substances behave.
There is a really clear difference between physical and chemical properties. Physical properties are all about appearance, right? Like, does it shine? Is it hard? Can you bend it? But chemical properties? Well, that's all about action. It tells us how a substance acts when it literally bumps into other things. Today, we're going to play the role of scientists. We're going to expose our metals to oxygen, water, acids, and salt solutions just to decode their true, hidden personalities.
Moving right along to Section 2, metals reacting with oxygen. I like to call this one the trial by fire.
The fundamental rule here is super simple. When metals react with oxygen, they form something called a metal oxide. And for the most part, these metal oxides are basic in nature. That means if you dissolve them in water, they form bases, like how magnesium oxide dissolves to become magnesium hydroxide. But, and this is crucial, not all metals react with oxygen in the exact same way.
There is actually a massive contrast in how different metals handle oxygen. Let's look at magnesium. If you burn a piece of magnesium ribbon, it doesn't just sit there. No way. It produces this incredibly bright, dazzling white flame. It's a really explosive reaction that just leaves behind a white ash, which is our magnesium oxide. So magnesium plus oxygen gives you magnesium oxide. But then, look at copper. When you heat copper in the air, it definitely doesn't burst into flames. Instead, it just slowly, quietly forms this dull, black coating of copper oxide. Copper plus oxygen yields copper oxide. It's a way slower, much calmer personality.
Now, I mentioned earlier that most metal oxides are basic, right? Well, there are some fascinating exceptions you absolutely need to know about. We call them amphoteric oxides. These are metal oxides that have a sort of dual personality. They can actually behave as both acids and bases. Aluminum oxide and zinc oxide are your prime examples here. They'll react with both acids and bases. Listen up, guys. You're going to want to remember this because it is an incredibly common board exam question.
All right, Section 3, metals reacting with water. From violent splashes to absolute silence.
This perfectly illustrates the massive range of behaviors we're dealing with. Up at the very top, you've got sodium and potassium. They react violently just by touching cold water. Calcium is a step down. It definitely reacts, but a bit less vigorously, forming calcium hydroxide and releasing hydrogen gas. Now drop down to magnesium, and it's much lazier. It reacts super slowly with cold water. It really needs hot water to get going. Iron won't even react with hot water. It literally needs steam. And down at the very bottom, copper, silver, and gold. Absolute silence, zero reaction whatsoever.
Let's zoom in on that top tier for a second, because it is wild. When sodium and potassium hit cold water, they produce a massive amount of heat and release hydrogen gas. So, sodium plus water gives us sodium hydroxide, hydrogen gas, and just a huge amount of heat. It is a highly aggressive reaction. And hey, this right here perfectly answers the first part of our opening mystery. Because of this violently high reactivity, sodium and potassium absolutely must be stored in kerosene oil. If you just leave them sitting out on a desk, the tiny bit of moisture in the air is literally enough to set them off.
Jumping right into Section 4, metals reacting with acids, or releasing the hydrogen.
Okay, here is the core mechanism you're going to want to memorize. When a metal reacts with a dilute acid, it forms a salt and it releases hydrogen gas.
What's actually happening behind the scenes is that the metal is displacing, basically kicking out, the hydrogen from the acid, and that displaced hydrogen just escapes as a gas.
For instance, if you drop a piece of zinc into hydrochloric acid, you are immediately going to see bubbles appearing. Zinc plus hydrochloric acid gives us zinc chloride and hydrogen gas. That bubbling you're seeing? That's the displaced hydrogen gas making its escape. But of course, there are always exceptions. Copper, silver, gold, and platinum, they don't react with dilute acids at all. Why? Simply put, they are less reactive than hydrogen itself. They just don't have the chemical muscle to kick the hydrogen out of the acid. So our lowest energy metals just stay completely unbothered.
Moving along to Section 5, Displacing in Salt Solutions. This is basically the battle of the metals. To really understand this battle, we need to know what a displacement reaction is. This is a chemical reaction where a more reactive metal displaces a less reactive metal from its salt solution. You can think of it exactly like an arm wrestling match. The stronger, more reactive metal walks in and just steals the salt right away from the weaker, less reactive metal.
Let's see how this actually plays out in a real experiment. In step 1, we start with this beautiful blue copper sulfate solution. Then, step 2, we drop a piece of zinc metal right into the beaker. And in step 3, the magic happens. The solution gradually loses that blue color entirely, and copper metal just gets deposited right at the bottom. Chemically speaking, zinc plus copper sulfate yields zinc sulfate and copper. This proves beyond a shadow of a doubt that zinc has the dominant personality here. Zinc is way more reactive than copper, so it literally kicked the copper right out of the solution.
And finally, Section 6, the reactivity series, the master ranking.
Here it is, the reactivity series ladder. Scientists took all these behaviors we just looked at and arranged the metals strictly according to their reactivity. Right at the very top, we have our explosive, highly reactive elements, potassium and sodium. As we step down the ladder through calcium, magnesium, aluminum, zinc, and iron, you'll notice the reactions get slower and way less aggressive. Then we cross the hydrogen baseline, and right at the very bottom, we find copper, mercury, silver, and our immortal champion, gold. It perfectly maps to every single personality test we just talked through.
But you might be wondering, so what? Why does this master ranking actually matter to us? Well, because understanding these chemical properties is literally the backbone of modern engineering. Thanks to this series, we can predict reaction speeds. We know exactly which metals we can extract from ores and how to do it. It tells engineers what metals to use to manufacture your cooking utensils so they don't dissolve right into your dinner. It tells us how to build durable vehicles and how to prevent structures from corroding. This list is literally the blueprint for building our physical world.
Which brings us right back to where we started. Based on everything you've learned today about oxygen, water, acids, and the master reactivity series, why do you think sodium absolutely has to be stored in kerosene oil, but gold does not? I want to officially challenge you to write your absolute best scientific answer down in the comments section below. Thank you so much for joining me today for this deep dive into Class 10 science. Keep learning, keep exploring, and make sure you tune in for Part 3, where we're going to switch gears entirely to learn all about the chemical properties of nonmetals, ionic compounds, and how ionic bonds are actually formed. See you next time on The Explainer.